Hello everyone. It is a great honor to participate in 2023 IFAC World Congress. I'm Gugyeong from the HRC-Lab at the Yeungnam University. Today I'd like to talk about how we can improve working autonomy in people with paraplegia who use powered exoskeletons. Each year, hundreds of thousands of people worldwide experience spinal cord injuries, with only a small percentage achieving full neurological recovery. Unfortunately, many patients face severe skin and digestive system damage due to immobility. As a result, it leads to higher mortality rates compared to the general population. However, through periodic treatment and rehabilitation, they can significantly reduce mortality and improve their quality of life. Powered exoskeletons have gained considerable interest as assistive robotic devices for people with paraplegia. These devices need to provide robust gait, stability, balance, weight transfer, and user safety while being compact, lightweight, and energy efficient. Various powered exoskeletons have already been commercialized, each with its own features. Mainly two types of powered exoskeletons exist by using crutches. Atlante and Rex are the representative crutchless powered exoskeletons, and crutchless powered exoskeletons have an advantage in hands-free while walking, but they are heavy and bulky. Powered exoskeletons using crutches have an advantage in wearability since they have less weight and volume, but they should focus on using crutches while walking. Today, I'll focus on powered exoskeletons that use crutches as they offer the potential for improving walking autonomy. In spite of the advancements in powered exoskeleton technology, there is still room for improvement. Currently, users require additional assistance to control their center of mass while walking. As shown in the videos, insufficient propulsive force and gait instability hinder independent walking without external assistance. Therefore, our goal is to explore how gait patterns using crutches in powered exoskeletons can address these challenges. One of the crucial aspects in designing the gait pattern for powered exoskeleton is ensuring a number of active degrees of freedom to apply the gait pattern. People with paraplegia have a lack of lower limb mobility, so most powered exoskeletons with crutches have active degrees of freedom at the hip and knee joints, and passive degrees of freedom at the ankle joint. However, applying the gait pattern used by able-bodied individuals to powered exoskeletons with crutches may result in the user's center of mass being positioned further back since they cannot control their center of mass. It determines the center of mass movements forward. Additionally, relying on the external assistance such as physical therapies affects the user's walking autonomy. Our hypothesis recognizes that people with paraplegia have distinct abilities and training goals when using powered exoskeletons. So we need to develop specific gait patterns to achieve independent mobility, considering their unique requirements. Our proposed gait pattern involves a slight tilt of the user's trunk, which creates a wider and more stable crutch position. Therefore, it improves the user's ability to walk independently. It is important to understand the characteristics of people with paraplegia to apply new gait patterns effectively. Due to long-term lower limb inactivity, people with paraplegia experience significant muscle loss in their lower limbs. This results in reduced weight in the lower body and shifted the center of mass towards upper body, unlike the center of mass of able-bodied individuals located near the pelvis. Additionally, prolonged inactivity leads to joint contracture and ankylosis. Powered exoskeletons may only have two stages, standing and walking. Walking further comprises the stance and swing phases. To apply the proposed gait pattern, we need to determine the standing posture and the initial and final foot positions of powered exoskeletons. Since the stance and swing phases are repeated, we could define the initial swing foot is the terminal stance foot. The stance phase is determined by external environments such as gait speed, strides, or ground conditions, and swing trajectory is determined by data activity. Since most powered exoskeletons with active degrees of freedom in the hip and knee joint cannot fully respond to the actual movement of center of mass. So crutches must be utilized to control the user's desired movement. Our proposed standing posture aims to provide a larger stable crutch region by placing the center of mass closer to the leading foot position and slightly tilting the body forward. This ensures a more stable standing posture regardless of standing motion conditions. Since people with paraplegia experience the joint contracture, we very carefully designed the range of motion for powered exoskeletons based on the each user's joint condition. We created mathematical models to design the joint angle trajectories. In the swing phase, the trailing leg moves from the air to the ground for the next step. To maintain stability, we must define the swing trajectory based on the mathematical models that assumes an imaginary tilted ground. This ground supports the elastic forward movements of the trailing leg during the swing trajectory. While the trailing leg swings, the loss of one of the 4 points causes, which comprise the base of support. To ensure stability in dynamic situations, we utilize the zero moment point, ZMP, to be within the base of support. This reduces the impact between the trailing leg and the ground at the end of the swing phase. So the results of our study show that the pilot using the proposed gait pattern achieved increased stride length and initial frontal acceleration. This means the proposed gait pattern allows to walk further and improve mobility. In fact, each 1 degree increase in the trunk inclination angle led to a maximal 16% increase in the initial frontal acceleration. So in conclusion, our study aimed to enhance walking autonomy in people with paraplegia wearing powered exoskeletons. While powered exoskeletons have great potential in supporting people with paraplegia to regain walking abilities, it is crucial to consider their unique abilities and training goals. By implementing innovative gait patterns like the one proposed, we can significantly improve their walking autonomy and independence. Thank you for your attention.
Yep. Now we have a